So now, so last time we were learning about this Taylor Lagrange inequality. So basically what we want to do is we want to find some concentration around median. But we want to do, concentration of certain, let's recall what we were doing. Maybe we need a bit more space. So basically we want to consider random graph and say we consider some function on the graph. And we want to show that this function is concentrated. And how we want to do it is that this is concentrated around median M. And how we want to do it is we consider all the graph whose F value is at most M. Then this take up half of the measure of this probability space. Let's say this is probability space consisting of all possible graph, and each of them are graph, and each graph carries out certain measure, and which sums up to 1. Each of them has for this fixed G, we have the probability that its G is same as G and P, which is the measure of this 1 point. Anyway, with that, if we take this median point M, then by definition measure of this is half. It could be a bit over half because of the definition of median. So this is definitely over half. And how we want to show it is that let's say this F is Lipschitz, meaning that once we change the edges, one edge, then the value of F may change by at most 1 or by some constant. If you take a K Lipschitz, say, then it differs by at most K. And every time you have a graph, and then if they are differ by just one edge, then the Hamming distance between them is 1. Here we consider each graph as a coordinate of 0, 1 vector, where each coordinate corresponds to a pair. So it's 0 if there is no edge in that pair. If it's 1 if there is an edge in that pair. Then you can measure by Hamming distance. And if you show that if you take this, let's say this is A, and then if you take all the points which is Hamming distance at most T from this A, then with this assumption, if this has measured at least 1 minus epsilon, then we can say that with probability at least 1 minus epsilon, we know that the F of G is at most M plus KT. Because all this graph, which takes up at least 1 minus epsilon, measure of the entire probability space, satisfy that they are from a graph with F value at most M, and by changing at most T adjacency and other adjacency, and each time you change at most K. But what we want to do is we want to improve this further. Because in this Hamming distance, every coordinates are symmetric. They are they are not really distinguishable. But depending on this F, let's say if we want to count the number of triangles, or in this graph, if you change this edge, then it doesn't hurt the function F, which counts the number of triangle. But if you change this, then it actually hurts. It actually changes the value of F. So some coordinates are more important and some coordinates are less important. So we want to consider other types of distance, which measures over all weighted, situation. So some coordinate carries more weight than the other coordinate. That's a weighted situation. And we want to be able to deal with, all possible weighted situation. So what we do is we consider the product probability space, and then we consider A there, which is a subset, and consider a vector. And we want to measure the distance between this point and this set A. How do we do it? Is that when alpha 1 to alpha n, which is the weight on each coordinate, how important it is, are given, we can consider the weighted distance between y, some points y and x. If we have y, say y, and x, then if these two are different, then in the Hamming distance we have to add 1. And these two are different, 1. So Hamming distance between them is 2. But now each coordinate carries out this weight. So this is different, so we want to add alpha 1. This is different, we want to add alpha 5. So we want to say that this is the weighted Hamming distance between these two. So this is that. But we want to consider all possible alpha. So let's say we fix the alpha, and we want to measure the distance between x and a. Then how do we measure it? We have a and x, and we want to measure the distance between points x and all points y, and we take the minimum one. So this is weighted distance between x and a. And we want to take the worst case over all weights. So if we know this, then whatever weight we are given, we can say that with that weight, the weighted Hamming distance between x and a is at most this value. So this is the definition that once we compute this, say this is some number beta, then no matter how the weight is given between x and a, we can always ensure that the weighted Hamming distance between these two with this weight is at most this beta. And this number is, among all those value beta which has that property, this is the one with the smallest value. And let's write a sub t to denote all the points which has a distance at most t from a under any weights given. And with that, Taylor-Lagrange inequality is saying that this holds. Whatever set A, and this probability A is again the measure. In this probability space, the measure of this A. In other words, if you choose one point at random according to this probability space in here, then that's the probability that your randomly chosen one lies inside of A. So this is what we want to prove. So in order to prove that, let's define some terminology. So as we are dealing with these points in this product space, and from that, we have some, coordinates. So here it's 0, 1, but it doesn't have to be 0, 1. This each of omega I could be anything. So from here, all we care is whether this and this are same or not, and if this and this are same or not. So what we want to do is we want to kind of, translate this setup into some, some space that we are familiar with. And in that space that we are familiar with, we want to, use some linear algebra or some, linear algebra to, convert this concept of distance into something that's more comprehensible. So this is defined as a supremum or minimum of this, which seems a bit difficult to actually deal with. So what do? Is we consider this set U of AX. So we consider all the 0, 1 vector such that, we collect all the vectors such that there exists Y such that Xi and Yj, Yi is different. Give me a moment. Let me quickly check something. Yeah, okay. So what we do is this. Let's write it in the next line. This implies that Si is 1. So let's say A consists of, say, 2, 1, 2, 2, 1, and X is, let's say 2, 2, 0, 1, 0. And X is, say, 2, 2, 0, 2, 1. So if we choose this Y and this X, then it's different on the second coordinate, third coordinate. So we consider this 0, 1 vector, or let's write it this way. So we consider all possible 8 vectors satisfying this. So this is either 0 or 1, 0 or 1, 0 or 1, so there are 8 such vectors. If we have that, then if we choose this Y, then this condition satisfies. So between this and this, these two are different, these two are different, and then these two are different, so we don't care what these are. So those 8 vectors lies in here. And also, if we consider this and this, then the last 2 coordinates are different. So if we choose any vector which looks this way, again there are 8 vectors. All 8 vectors lies in here. So that's the definition of this U. So if we have S, so say this is S, then 2, 3, 4 actually contains a set of coordinates we need to change from X to get to A. So in order to, you have X and A. If you want to, reach A from X, then what do you have to do? There are several ways. That one way is that you change this to here and you change this to here. And each changes in coordinate costs 1 Hamming distance. So, I mean, you recall this second coordinate, third coordinate, and that's a subset of, this coordinate of S. So you have this. So why we consider this is that if you have S in here, which is, so for technical reason, we are writing in this way so that it's actually more convenient for us to deal with such situation later. So here, instead of just putting 0, 1, 1, 0, 0 here, we actually allow to change this into 0, 1, 0, 1, 0, 1. It doesn't matter, right? But intuition-wise, so that's for technical reason, but intuition-wise, if you have exactly 0, 1, 1, 0, 0, then the Hamming distance between this corresponds to y. Then Hamming distance between x and y is exactly the number of ones in this vector. Wait a moment. And and what's the weighted Hamming distance? If we have weights alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, then weighted Hamming distance between x and y is S dot product with alpha. So, so considering these points actually provides us to translate these into some other term that we are familiar with, which is dot product. And here we are allowing this to change to some higher number, but that only, makes this larger. So when we take this minimum, they will never be taken. So, intuitively we can see that adding more points, adding all those points instead of just taking one point will not harm us in this, analyzing this. Because, whenever we take this minimum, this y and this minimum in y and minimum in s are gonna give the same answer, because whenever we choose the s which makes this minimum, then that s actually corresponds to 0, 1, 1, 0, 0 instead of this vector or other type of this vector. So using this, we can prove the following. Before explaining what the following is, let's define, say, V of AXB, the convex hull of U of AX. So here convex hull is the smallest convex set that contains this. So what it means is that here we have a 0, 1 vector, right? But instead, we consider it as so let's consider this lies in R to the n. So these are all also the vectors in R to the n. So in there, these are collection of points, and we consider the convex set containing this. We take the all convex set containing this, and then we take the intersection of all such convex sets. Then that yields the smallest convex set containing all of them. So that's this. So this simply consists of all the points, all the vectors, which are convex combination of this. So with this, we can prove the following alternative characterization. So this law of AX is nothing but the minimum norm of the vectors in this V, which is a convex combination of this U. So why would it be true? Let's consider some easy example and then see some intuition. Let's say you are in R2, and then you have, say, some points, and you get this convex combination. So this is convex Hull. And let's say, you have this point and this point and this point and this point. That point, let's say they all lies in U. And then let's say they all correspond to this, sets points in A. They all come from there. And once you fix alpha, then it's like you fix direction. So let's say alpha is this or this, it doesn't matter. So this unit vector or this unit vector is alpha. Then what are you trying to measure? You want to measure alpha dot product with S. That means here you consider this as a vector. Then you take the projection here, then this is the length. And for this, you have the length here, and for this, you have this length, for this, you have this length. And all those one, you get to choose which point. So you actually get to choose which point you are taking. So you want to minimize it. So you want to minimize this. So for this specific direction, you get this length. And then we want to consider the worst alpha, so where this gets longer and longer. But if you consider other direction, if you slightly rotate this, then you can actually see that this length, when you project this length gets longer, while when you project this length gets shorter. So if you keep rotating it, then at some point, when this is perpendicular, you get that once you project this, then you get this length. Once you project this, you get this length. Once you project this, you get a longer length. So this length is the smallest, this dot product. So worst, you consider the, so it's the biggest dot product among all alpha, where you take the smallest choice of this vertex. And that's where exactly you get in this convex hull, you choose the one with the smallest norm, which is the distance from here to 0. So hopefully that can provide you some intuition why, this should hold. And now we have to kind of make this more rigorous. And yeah. So let's say that there is this V, which is in this V, achieving the minimum. So this is the V. And as we did here, we consider the line from the origin to this V and a hyperplane, this one, hyperplane P through this B which is orthogonal to the line. So the purpose of this is kind of clear because every point who lies this side of this hyperplane has a bigger dot product. So when this is alpha, and this dot product with alpha, this dot product with alpha has a bigger value than this, right? So in order to separate that, we put this hyperplane P. Then P actually separate all of this from the origin. I mean, some points in here can intersect with P, but all of them lies on this side union with the hyperplane itself contains this. So for all S, if you take the vector from this B, satisfies this. So this is what you get here, and this is technically you have to like divide it by size of B, then you get this length and you get this projection. So from that you can actually get this. So let alpha be the vector corresponding to this direction. We have to normalize this. Then for all S which is in U, which also lies inside of this V, simply satisfies alpha dot product with S is at least this, which has size same as the norm of the vector V. So what was the definition of this law? Law was this. This is overall supremum of this choice of alpha, but we just calculate for one choice of alpha, and we calculate this, and its minimum is bigger than the size of V. So this provides one-side inequality that the law of AX is actually bigger than minimum, this V, say, which is this minimum. So we get this inequality. Now we want to show the other inequality. So we take any alpha, which is a normal vector, then give me a moment. Let me check. Yeah. It seems that I think I kind of said it wrong at some point that the sum of alpha 1 to alpha n sums up to 1, which was wrong. So we have to consider so instead of just, making sure that the sum of alpha 1 to alpha n is 1, what we are doing is that this vector has a size 1, meaning that alpha 1 square plus alpha 2 square to alpha n square is 1. So that's, how we consider this weighted Hamming distance. Anyway, so so where were we? Yeah, that's why we are keep taking the vector with the size 1. So now we have this, then what do we know? Then we know this. So we already taken this direction. If we have taken another direction, which color would be good? Let's say this direction. Then we have this inequality. So from alpha, you take a projection, then this length is smaller than phi. Now what do we know? We assume that as we have that this V is actually in this convex hull of U. So this one vector does not lie inside of, it does not correspond to a point inside of A, but it corresponds to a convex combination of other vectors which correspond to points inside of A. So we may write B is summation of lambda I, say Ti, for Ti or in U, and lambda I positive, and summation of lambda I is 1. Then what do we have? Then this can be rewritten as this. Again, we know that the dot product with alpha with T, with the points which lies inside of U has a meaning. That was this weighted Hamming distance in here. So this was, we have this, but this has no meaning because B might not be corresponding to a point inside of A. So we instead, consider this, transfer this into the, summation of the vectors inside of this U. Now this has meaning. And what's the meaning? So each of them is actually same as a weighted Hamming distance. But we have this, and then we know that summation of lambda is 1. That means there exists I such that this alpha dot product with Ti is smaller than the norm of B. Because otherwise, if this is strictly bigger than this for all I, then this has all value bigger than V, bigger than this. And then you take the weighted average, then it should be bigger than left hand side, which is contradiction. So there should be at least one such I. Then what does it mean? It means for any alpha, which is unit vector, there exists some points in U with, so this and this are the same vector, and it satisfies this condition. So which was the same as the summation of alpha I, and which correspond to Y in A, and which correspond to this. So this shows that this is at most size of B. So which prove this inequality. So we have this theorem. So now we have this theorem, and then what we want to prove is prove the Lagrange inequality. But how do we want to prove it? We choose x at random from omega. Then what we want to prove is that the probability of getting points inside of this omega minus at is exactly the probability that, let's say, x is the distance between this randomly chosen point and a. Then this is same as the probability that this random variable x is at least t. Then this can be rewritten in this way. So this is the typical trick. Instead of this, you consider the exponential power of this random variable. And now we use the Markov inequality to get this. Now what we want to show? We wanted to show that this, so Lagrange inequality says that this is probability that the omega minus at is at most this times this divided by probability of a. So we want to show that this is at most 1 over probability of a. So that's what we want to show. So now we want to show that by proving this theorem. So if you rewrite this expectation, then x is random variable, which is this. So this is exponential of quarter times this distance square. And then you have to take the expectation of this, meaning that you take the integral over all omega, and you compute this. So this is what we want to show. So now it suffices to show this. So as soon as we prove this, then we are done. So now we prove this in the next video.